separable equations. Separable equations are equations that can be put in the form y prime is equal to some function of x times some function of y. So let's start with an example and we'll see what we're talking about. Here we go. Here I've got y prime. So first off, this is a technique that is generally applicable for first order equations, y prime. But the equations don't have to be linear. So this is a technique that's generally applicable to first order equations, but the equations don't have to be linear. So let's start with an example. So I've got y prime is equal to 5y squared minus 2xy squared. Now the first thing I can see is that if I factor out that y squared, I can make it y prime equals a function of all x's times a function of all y's. That's going to let me put all the y's on the y side and the x's on the x side. Let's see what I mean by that. The first thing is, let's switch our notation. That y prime is very good, very useful because it's concise, but it means dy dx. And I'm going to replace the y prime with the dy dx in this case because I want to have two pieces. I want the dy side and the dx side so that I can multiply up, almost like cross multiplying. I can multiply up that dx to the other side. Now I've got a y side and an x side defined by the dy and the dx. They both have to be, the dy and the dx both have to be on ground level. So now I've got my x side and my y side. So let's put all the y's on the y side and all the x's on the x side. Alright, now I've divided both sides by the y squared. That's why it's important to be able to factor the y prime into a piece that's dx and a piece that's dy. Notice how I've got it into this form. A bunch of y's, some function of y's, here h of y times dy equals some function of x, g of x, some function of x times dx. Now, I can just integrate both sides. An equation is still an equation if I do the same thing to both sides, and the thing I'm doing to both sides of this equation is integrating. The difference being the y side I'm integrating with respect to y, it has a dy there, and the x side I'm integrating with respect to x. So on the y side it's going to be add one of the exponent, divide by what's up top, straight power rule. And on the x side I'm integrating with respect to x, and I need a constant. I only need a constant on one side because if I did put a constant on both sides they would get absorbed into the 1c. Now I'm done. There, it's integrated. All that's left to do now is maybe they give me an initial condition which will let me figure out the c, or maybe they're asking me to solve for the explicit solution. Right now I've got the implicit solution because it's written as a function of x and y. If I want it to be a function of, it's written as an implicit solution, the x's and the y's are all jumbled up together. If I wanted it as the explicit solution, I would solve for y. I would write y equals explicitly a function of x. So I guess in that case that would be y is equal to like minus 1 over 5x minus x squared if I solve for the y. Now this is an explicit solution. Notice that I put the c on exactly when I integrated both sides. I didn't integrate, solve for y, and then just tack on a plus c. That would have given me the wrong answer. The c would have been in the wrong spot. So, a separable equation is a first order differential equation that I can put in the form all my y's times dy equals all my x's times dx. let's go through and do some examples and see this working. Well, first thing, I see it's a y prime, and I see it's nonlinear because of the y squared. But I can separate it. I can put all my y's on the y side times dy equals all my x's on the x side times dx. So I guess the first thing I did then, before I did any separating, is I replaced that dy, I replaced that y prime with the dy dx. Then I can multiply the dx up, defining what's my x side and what's my y side. Now all I have to do is integrate both sides. Integrate the y side with respect to y, integrate the x side with respect to x, then tack on a plus c, integrating at the step that I integrate. Now, it doesn't say explicit or implicit solution, so I guess I'm done. If I wanted to solve for the explicit solution, I just take the tan of both sides. Remember that if I'm integrating 1 over x, it becomes ln of absolute value of x. Now, the technique itself is not difficult. Where I find that students stumble on this technique is the integrate both sides. Sometimes the integration is done incorrectly. So you do want to review your integration rules. You know, the derivative of tan is sec squared, so if you integrate sec squared, you get tan, that kind of thing. Let's take a look here. This one's first order. Oh, I've got an initial condition. So the first thing I'm going to do then is, if I cross multiply, I can cross multiply the dx up, cross multiply the y up, and now I've defined the y side and the x side. Integrate both sides. Integrate the y side with respect to y. A straight add 1 to the exponent, divide by what's up top. Integrate the x side with respect to x. A plus c. Now they've given me an initial condition. When x is equal to 0, y is equal to minus 1. So that's going to let me figure out what the c is. When I make y equal to minus 1 and x equal to 0, I make y equal to minus 1 and x equal to 0, I get that c must be equal to a half. So now my complete solution, my explicit solution, my unique explicit solution, and of course if I turn to the back of the book, they'll have probably have multiplied the whole thing through by 2 just to get rid of fractions. So you might see y squared equals 2x minus x squared plus 1 as an equivalent solution. Now, that's an explicit solution. Let's solve for the implicit, that's the implicit solution, because y is implicitly defined as a function of x. Let's solve for the explicit solution. So I'm just going to take the square root of both sides. Y is equal to, plus minus the square root. So if I go in here and I'm thinking about plus minus, but which is it? Or is it both? It's not both. It's one or the other. I go back up here and the initial condition tells me that y is equal to minus. So it's not plus minus, it's explicitly the minus. Y is equal to minus. Now why can't it be both? Well, let's think about it. if y starts out at negative when t is equal to 0, or when x is equal to 0, and they tell me that's the case, when x is equal to 0, y is equal to minus 1. If it starts out as negative and it somehow becomes positive, then it must be 0 somewhere in between where it's negative and where it's positive. But y cannot be equal to 0, because if I go back up to here, that'll give me an infinite y prime. I'd be dividing by 0. So we're actively choosing the negative as an explicit solution. It's a small picky point, but it's important. And if I put in the x equals 0, I do get out the y equals minus 1. It goes through the initial condition. Let's see another example. Well, this next example, it doesn't immediately look like it could be separable, but I can factor this side. And I might not see that I can factor it, but I would see that it's first order. It's first order linear, so I could also solve it as a first order linear differential equation, but I'm looking at it as an example of a separable equation. So I want to write it then, if I'm trying to write it as a separable equation, I'm trying to write it as y prime is equal to some function of x, and if I collect on this y, let's factor out, let's move this piece over here and factor out the y. That would be y times 1 plus x minus 2 minus 2x. And now I can see, I can factor out a minus 2 out of that side. And across this minus sign, I see I can factor an x plus 1 or 1 plus x bracket. Get y minus 2, x plus 1. So I can see I can write y prime or dy dx as some function of y's times some function of x. Now I see it's a separable. I can multiply up my dx, divide out the y minus 2 bracket, and now I'm set. Integrate both sides. Absolute value of y minus 2 equals x squared over 2 plus x plus a constant. Now, I can't figure out that constant because they didn't give me any initial conditions. If they did give me an initial condition, though, they would tell me what y is equal to. Say that they said that the initial condition was when x is equal to 0, y is equal to 5 or something. Well, they're telling me that y is equal to 5. They're telling me that y minus 2 is on the positive side. So if y minus 2 is on the positive side, I should replace those absolute value bars with just straight brackets because y is greater than 2. If, on the other hand, they told me that the initial condition was y equals 0 and x is equal to, 1, in that case, if y was equal to 1, then the y minus 2, the 1 minus 2 would be negative, so I would replace those absolute value bars with minus a bracket. So I'm picking a side. These absolute value bars are either doing nothing if the y minus 2 is positive, or they're multiplying that whole y minus 2 expression by minus 1. Just like we picked a side up here for this, with this example, whether we picked a positive square root or a negative square root. This last example is, well, what's the point of this last example? the point of this last example is the technique itself, the separable equation technique, we can still do this even though we can't integrate it. I can see that I can replace this y prime with a dy dx, so I can multiply up the dx, defining my dx side and my dy side. So I've got all my x's times dx on one side and all my y's times dy on the y side. As long as I do the same thing to both sides, it's still an equation. So the thing I'm doing to both sides is integrating. I integrated the y side with respect to y, and I integrated the x side with respect to x, except that I can't integrate e to the x squared. That's one of those ones that can't be done by us. So the best I can do is just leave it and tack on a plus c. Maybe I could square root both sides, plus minus if I'm looking for plus or minus if I'm looking for the explicit solution. But what I've come up with now then is an implicitly defined solution, which is as best as I can do with this particular example.